Today's topic of discussion is obtain an equation of orbital time period of a satellite revolves around the earth. Okay. Now the period of satellite is the time it takes to make one full orbit around the earth. Okay, so time required by a satellite to complete one revolution around the earth is nothing but a time period. And as you know that orbital period of satellite, as such orbital velocity, which we have already derived last time, okay, that orbital velocity is given by, this is orbital velocity, that is given by this formula, that is v0 is equal to gme upon re plus h and square root of it. Now try to understand. Here this is the radius of the earth and say this is the height of the earth. Height from the earth, that of the satellite. Height of the satellite from the surface of the earth is h. So total distance is re plus h from the center of the earth. Okay. So this distance sometimes is denoted by r. Okay, so sometimes we use small r instead of this re plus h. Okay, that you keep in mind. Okay, so orbital velocity, that is given by under root of gme upon re plus h, where h is the height of the satellite from the surface of the earth and re is the radius of the earth. Now this orbital velocity is nothing but circumference of orbit of satellite divided by the time period. So this becomes v0 or vo, orbital velocity. vo is equal to 2 pi re plus h, because the circumference of the circle is given by 2 pi r. And instead of this r we write re plus h. So it becomes 2 pi re plus h. Okay. So 2 pi into bracket re plus h divided by the time period. Now these two equations, you can see equation 1 and equation 2 are same. They are giving the orbital velocity. It is giving the orbital velocity. So comparing them, we get under root gme upon re plus h is equal to 2 pi into bracket re plus h upon t. And if you make t as a subject of formula, okay, then the new equation can be written as, okay, t is equal to 2 pi re plus h upon this whole bracket will come, that is under root gme upon re plus h. Now this re plus h, which is there in the numerator, can be written as re plus h the whole square and square root of it. And if it is written like this, then this re plus h, which is there in the denominator, will go in the numerator. Okay, and it will be multiplied with this. So it becomes under root re plus h the whole cube and square root of it. Okay, so it is written like this. Okay, and under root, okay, it is taken as under root re plus h the cube upon gme. Now squaring this, you remove this square root. Okay, so t square is equal to square of 2 pi will become 4 pi square. This will come out of the square root, so it becomes gme, and here this becomes re plus h whole cube. Okay, so both the way it can be written, or if you take the square root of it, then you will get the time period. Okay, now as you know that gme upon re plus h the whole square, or rather we can say gme upon r square gives you the value of gravitational acceleration at that point where the satellite is situated at distance say r. R is nothing but re plus h. Okay. So instead of this gme upon re plus h the whole square, we can write small g. Okay, so this equation number 5 can be written as t is equal to 2 pi under root re plus h upon g. Okay, it is very easy to understand. Okay, now fourth equation, you can see this fourth equation. Okay, this is the fourth equation. In this fourth equation, this 4 pi square upon gme is taken as constant, so t square is equal to k, and instead of this re plus h, as I have explained earlier, it is written as r, so it becomes r cube. So we can say t square proportional to r cube. Okay, that is explained here. Okay, which is nothing but the third law of Kepler for the planetary motion. Okay, now if the satellite is very close to the surface of the earth, okay, then this very close to the surface of the earth means h is equal to 0. Okay, in this equation number 6, if you take h is equal to 0, then you get the equation t is equal to 2 pi under root re upon g. And if you place these constants, okay, g is 9.8 meter per second square, re is the radius of the earth, that is 6400 kilometer. Okay, 6400 kilometer. So if you convert it into meter, then it becomes 6400 into 10 raised to 3 meter. It is not meter per second, but it is meter. And if you place these values here, then the time period of the satellite very close to the surface of the earth is found to be about 85 minutes. Okay. Now there is a question: obtain an expression of total energy of satellite revolving around the earth. Now let us consider a satellite whose mass is small m. Okay, and it is revolving around the earth at a distance r from the center of the earth. So we can say here, we can understand r is equal to nothing but re plus h, that is understood. Okay, and the orbital velocity is VO. Orbital velocity is VO. Now see, potential energy, that is gravitational potential energy of the system of earth and satellite. The masses of earth and satellite are me and m respectively. So that formula of potential energy is given by, try to understand here, this must be a negative, okay, because it is binding energy. So gravitational potential energy of the earth and satellite system is given by minus, try to understand, minus gmem upon r, where r is the distance of satellite from the center of the earth. So here take care, this is the negative value. Now as this satellite is in motion, the kinetic energy is 1/2 mvo square, where vo is the orbital velocity, and its value, as you know, it is gme upon r, having square root of it. Okay, so if this value is substituted here instead of v0 or vo, then you will get, okay, then you will get this equation of kinetic energy. Instead of this VO, we are putting this value, it is gme upon r, and having a square root, and square of it will give, then the square root will be removed. Okay, so 1/2 m, okay, and square of this, okay, that is shown here. Okay, so you can easily understand. So if you remove this square root and square, okay, so here kinetic energy will be gmem upon 2r. That is very easy to understand. Okay, it is GMEM upon 2R. Okay, where R is RE plus H, that is very easy to understand. Now total energy, that is potential energy plus kinetic energy. Now total energy is the sum of potential and kinetic. So potential energy we have already have the formula here. This must be with negative sign. Okay, minus GMEM upon R. Okay, so here we can write instead of this V as minus GMEM upon R plus this value that we have obtained, that of kinetic energy, that is GMEM upon 2R. And if you simplify this, okay, then this total energy is obtained, that is minus GMEM upon 2R. Okay, this negative sign is nothing but it shows that it is a binding energy of the earth and satellite system. Okay, negative sign indicates that satellite is in bound state to the gravitational field of the earth. Kinetic energy and potential energy at infinite distance will become zero, hence total energy will also be zero. To escape to initial energy equal to total energy or greater than this positive energy is given to the satellite. Rather, if you want to remove this satellite from the Earth's gravitational field, then you have to give the value of energy which is equal or more than this energy, and this must be a positive energy which is given from outside. Then the satellite will escape from the gravitational field of the earth. So external energy which is given must be positive, which is either equal to or greater than this value. Okay, otherwise the satellite is not going to go out of the gravitational field of the earth, and it will constantly rotate in the orbit. This indicates this satellite is in the bound state with the gravitational field of the earth. Okay, now what is binding energy of satellite? Write its equation. Okay, the minimum amount of energy required for a satellite to escape from Earth's gravitational field. Minimum amount of energy which is required for a satellite to escape from the gravitational field of the Earth or in gravitational influence of the Earth is a binding energy, and we have derived its equation. Okay, we have already discussed that it is minus GMEM upon 2R. Okay, so total energy of satellite is negative, that is showing its binding energy. And if you want to remove this satellite to infinite distance, then positive GMEM upon 2R energy must be given from outside. Okay, so binding energy of the satellite is nothing but GMEM upon 2R, where R is nothing but RE plus H, that I have explained. Okay, the radius of the earth is RE, and the height of the satellite, somewhere here is the satellite. Okay, this is the point where satellite is situated. So this total distance is nothing but RE plus H, which is here denoted by small r. Okay, so binding energy is given by this formula. Okay, that is GMEM upon 2R. Okay, that energy which is positive, that is given from outside to remove the satellite from the gravitational influence. Okay, now we talk about the geostationary satellite. Okay, so for remain geostationary orbit, obtain the equation of its height from the surface of the earth. So we want to find out at what height the satellite should be kept so that it becomes the geostationary satellite. Now, what is first of all geostationary satellite? If any Earth satellite having orbital periodic time of 24 hours, that is equal to the periodic time of the rotation of the Earth about its own axis, okay, then it appears always stationary as viewed from the Earth, and it revolves around the Earth in the equatorial plane in east-west direction. Then this type of satellite is a geostationary satellite. So its time period of the revolution, okay, is 24 hours, which is similar to that of the time period of the rotation of the Earth around, or rather on its axis, about its axis. Okay, so whenever you view this satellite from the Earth's surface, then that satellite appears to be stationary, and for this it is placed with a suitable height, that is, say that height is h from the surface of the Earth. So the satellite is kept at certain height, say h, and this is the radius of the Earth, that is RE. So total distance of this satellite from the center of the Earth will be RE plus h, that I have explained earlier also. Okay, and in general we know that the time period, as you know, there are certain calculations that I am showing it here. Okay, the time period is given by the equation, that is t is equal to 2 pi. This formula we have derived today itself, that is RE plus h the whole cube divided by GME, that is under the square root. Okay. Now if you take the square of this, then you will get t square is equal to 4 pi square, okay, RE plus h the whole cube divided by GME. Okay. Now if I make RE plus h cube as a subjective formula, then we can get RE plus h cube as it is on right hand side. Just for the sake I have written it on the left hand side, and you will get GME t square upon 4 pi square. Now taking the cube root, then this becomes RE plus h, and this is the cube root. Okay, so you get GME t square upon 4 pi square and cube root of it. Okay, now make h as a subjective formula, then this equation is obtained. So h, that is height of the satellite from the surface of the Earth, is given by this particular equation, that is GME t square upon 4 pi square and cube root of it. Okay, and this RE goes on the other side, so it becomes minus RE. Okay, so you can easily understand that height of the satellite is given by this particular equation. Now at what height we have to place this satellite, that is geostationary satellite? Then the definition says that time period must be 24 hour. Okay, so instead of this time we write 24 hour converted into second, and all these values, constant values are there. G is 6.67 10 to the power minus 11, ME is mass of the Earth. All these values are substituted, then the height is obtained nearly about 35,800 kilometer. Okay, and these satellites which are placed at a particular height which is obtained here, they are all used for telecommunication. Okay. Now, what are the conditions necessary for satellite to appear stationary that we have slightly discussed? Satellite having the circular orbit is in the equatorial plane of the Earth. Okay, its orbital time period of revolution must be 24 hours. The satellite must travel eastward, that is west east, at the same rotation speed as that of the Earth, and it should be at a height nearly about 36,000 km, that is 35,800 km above the equator of the Earth. The inclination of the orbit must be 0. Okay. Then comes the polar satellite. Okay, these polar satellites are at low altitude, about height which is 500 to 800 km from the surface of the Earth. That satellite are moving in a circular orbit, but they are moving or they go around the pole of the Earth in a north-south direction. Okay, so these are the satellites which are moving from pole to pole or north-south direction. This way they are rotating. The other one was east to west. Okay, it is a geostationary satellite. Okay, its time period is around 100 minutes. It crosses any altitude many times in a day. A camera fixed on it can view only small strip of the Earth in one orbit. Okay, adjacent strip are viewed in the next orbit or in the next revolution. Okay, hence in effect the whole Earth can be viewed strip by strip during the entire day. These satellites can view polar and equatorial regions at close distance with good resolution. Information gathered from such satellites is extremely useful for remote sensing, meteorology, as well as for the environmental studies of the Earth. Okay. Now, what is weightlessness? When a weight of the body becomes zero, or when any surface exerts a force on the body and reaction force becomes zero, then this body is said to be having the weightlessness position. Let us consider a spring balance which is hung through a ceiling, and on its other end mass of the body is suspended. The length of the spring is increased, and from that we can have the mass, or we can say weight of the body that we have seen. Now when the spring falls freely, try to understand, when the spring initially is hung this way and the object is kept here, its pointer shows some mass. Okay, some mass is there. Now when this is suddenly falling down somewhere, this is broken somewhere here. Okay, somewhere it has been broken. Okay, and what will happen? This will fall down, this will go down. Okay, and the motion of this spring is having the acceleration which is equal to gravitational acceleration. Okay, the motion is having the accelerated motion, and this acceleration is nothing but equal to gravitational acceleration. So whenever the spring falls down, the acceleration of the spring and mass system will have the acceleration equal to gravitational acceleration. Say for example it is broken from here and it falls down. Then at that time the weight which is seen, or rather the spring gives you the weight which is equal to 0, because the resultant weight, as try to understand, mg force is in downward direction and the pseudo force, that is mg, in the upward direction. Both the forces are cancelling out each other's effect, so resultant force will be equal to 0. So weight seen in this spring will be equal to 0. Similar thing happens when the person which is in the lift, okay, Say for example the lift is moving with some acceleration, and this acceleration of the lift is equal to g. Say this rope is broken, then what will happen? Mg force that of the person is in downward direction, and the pseudo force because of pseudo acceleration is in the upward direction, and both will cancel out each other's effect, and weight of the person is seen to be zero. That is called the weightlessness. Okay. Thank you very much, and here our chapter is ending. Try to watch all these videos 2-3 times, write the necessary things in the notebooks, and prepare the theory part properly. Okay, thank you very much.